Hi, we are continuing with our lecture on AET. So this might be the last class for module number 3, electromagnetic waves. So in the last class we have seen the normal incidence of plane wave on a boundary. In this class we are going to look at a more general form, reflection of a plane wave at oblique incidence. Oblique means at an angle. So before we go into the details, we need to generalize some more things. We have said in our previous lectures that the wave will be traveling in, let's say, Z direction, and E and H will be perpendicular to each other. Now we are going to generalize the direction of propagation of a wave. We define the electric field E is equal to some E0 cos of k dot r minus omega t. This is a general wave equation, a wave propagating in an arbitrary direction. It can be Z, it can be X, it can be Y, or it can be at some angle between X and Y, or X and Z, or Y and Z, or some angle with respect to all X, Y and Z. So it can be any general direction. So this is a wave traveling in an arbitrary direction. You see this k dot r minus omega t, it can also be written as omega t minus k dot r, because the cos of theta is equal to cos of minus theta. Okay. The k vector is defined as kx ax cap plus ky ay cap plus kz az cap. Okay, and the name of this vector is called as wave number vector or propagation vector. And r is equal to x ax cap plus y ay cap plus z az cap, and this is our normal position vector. Okay. So when you do k dot r, you will get kxx plus kyy plus kzz. So for example, in a lossless media, with EM wave propagating in Z direction, the k z is equal to beta, because it is in Z direction, and all the values of x and y will be 0, because it is in Z direction. So your k dot r is equal to beta z. So this is our wave equation that we have seen till now. Okay. Now the magnitude square of k is kx square plus ky square plus kz square. This is actually equal to omega square mu epsilon, which is equal to beta square. This is for lossless medium. So, using this general equation, you can find out the wave traveling in any particular direction, and all these things we have seen previously. So, all the wave in general can be written in terms of the propagation vector and the position vector, and this is the equation of the corresponding electric field. And the value of, for lossless media, the value of k is equal to, or the magnitude of k is basically beta. Okay. And you should also know that this k dot r is actually a constant. Because at any position x, y, z, kx, ky, kz are constant, which means kx x plus ky y plus kz z is a constant. Fine. Okay. So, this is the general form, and we are going to look at a wave incident on a boundary obliquely and find out what is the relation between electric magnetic fields in the two medium. So, before going into specifics, let us look at the following. So, let us say there is a boundary here, okay, and this is the z direction. I can draw it from here. Okay. Now, this is the boundary. Okay. Let us say the boundary is in x, and there is a y which is coming out of the paper towards you. Okay. And let us say a wave is traveling incident on z equal to 0 boundary, gets reflected, and some portion gets transmitted. Let the angle made by the wave, incident wave, be theta I. Let the angle made by the reflected wave be theta r. Let the angle made by the transmitted wave with respect to z is theta t. Now, we told that there is a position vector associated with each of the incident, reflected and transmitted wave, or the propagation vector. So, let us say the propagation vector for incident wave is ki, reflected wave is kr, and transmitted wave is kt. So, if you remember in our last lecture for normal incidence, we have drawn this boundary as a 2D figure, and we showed that it is actually a infinitely long boundary in which the wave is incident. Okay. Now, the k of incident, reflected and transmitted is now at some angle with respect to z, x and y. So, we need to make components of ki or kr, kt parallel to each of the axes. So, the first step is find the components of ki, kr and kt with respect to x, y, z axis. So how will you do this? So let's draw that k vector. Let's see how we can make the components. So ki is something like this. Okay. So I can make one parallel component, which is this, and one perpendicular component, which is this. Let me draw it correctly. This is one parallel component. There is a perpendicular component. And you see this angle ki makes with x-axis is or the z-axis is theta I, which is this. Okay. Because if you create a parallel line for z-axis at ki, you see this angle is also theta I, and which is what we have shown here. Okay. Fine. So I write my component along z as ki z, and component along x as ki x. Okay. The first medium, so this is medium number 1, and this is medium number 2. First medium we have epsilon 1, mu 1, sigma 1, gamma 1, beta 1, etc. Second medium will have epsilon 2, mu 2, sigma 2, gamma 2, and beta 2. So we have already told that ki for a lossless medium is beta I or beta 1, right? So I can write ki z is actually ki cos theta I, ki x is ki sin theta I, where ki is actually is equal to beta 1. Why beta 1? Because we are considering for a lossless media, ki is equal to kr is equal to beta 1. Okay. So here actually we are considering the magnitude. Let me make it clear. This is actually the magnitude of ki. Okay. So the magnitude of ki is actually beta 1, and the magnitude of kt, which is in the second media, is beta 2, which we have seen in the normal incidence case. Okay. Fine. So I can write the magnitude of ki z. Let me write it. The magnitude of ki z is equal to beta 1 cos theta, and the magnitude of k I x is equal to beta 1 sin theta I. Now let's look at kr. So you see the kr here is in this direction. So I can draw kr like this. This is kr vector. I can make this, so the magnitude of kr vector will be in this direction. So I can resolve into two components. So how will you resolve this into two components? So to resolve this, you need to go like this and go like this. So this is ki x because it's in the top direction, and this is ki z, but this ki z is in the backward direction. So this is KR. KRX and KRZ. Now KRX, the magnitude is towards up direction. So I think the previous one I haven't mentioned the direction. Okay, towards the up direction. So this is, and you see this angle is theta r from here. So KRX is equal to mod KR sin theta r, and KRZ is equal to mod KR cos theta r. And we know that mod KR is beta 1. So this is beta 1 cos theta r, and this is beta 2 sin theta r. Sorry, beta 1 sin theta r. Now let's look at KT. So KT is in this direction. So I'll draw in the same direction. This is KT. So the magnitude of KT will be like this. So I can make into two components. One along positive x z, another along positive x. Okay, so this angle is theta t. So if you look at here, this is theta t. So I can write this as the magnitude of KTZ, because it is parallel to Z, same direction of that of Z. And the one which is going up is KTX. Okay. So before going, let's explain that. Let me do one more thing. So you see in the previous derivation, the x is actually moving in minus x direction. This is minus x, sorry, minus z. So this is positive z, so this is negative z. So actually the value of KRZ is, there is a minus sign because it is moving in minus direction. Now coming back to KT, so KT Z is beta 2 cos theta t, and KTX is beta 2 sin theta t. Why beta 2? Because we already have proved that, or we have already told that for a lossless media, the magnitude of KT in the second medium is beta 2. Okay, and KT, magnitude of KTZ is magnitude of KT into cos theta t, that is beta 2 cos theta t. Okay. So in this way, you can resolve the propagation direction in the direction of your choice, so that it almost becomes similar to that of our normal incidence, and you can substitute the values and you will get the answer. Okay. Now if I write the expressions for electric field incident is the electric field magnitude, which consists of the direction also, cos of KIXX plus KIYY plus KIZZ minus omega t, where this term is actually from K dot R, Ki dot R actually, because we are considering the incident wave. And Similarly, I can write reflected wave as ER0 cos of KRX x plus KRY y plus KRZ z minus omega t. And ET is equal to ET0 cos of KTX x plus KTY y plus KTZ z minus omega t. Okay, where these all are magnitudes. These are all magnitudes. Okay. Now, when you apply the boundary conditions and tangential conditions, the only condition in which all this electric field will exist in the two media is when the first condition is when Kix is equal to Krx is equal to Ktx. Second one, Kty, or let me write in order, Kiy is equal to Kry is equal to Kty. So this with this conditions, the boundary conditions will be satisfied and EM wave exists in both media. A small bit of a derivation which I am not mentioning. So this is the condition in which the electric EM wave will exist in both first media and second media. So the components of the x components of K should be equal, and also the y components of K should be equal. Okay. You see that the Z component need not be equal because we are considering the wave is incident on the Z plane with Z equal to 0. Okay, so be careful in that. Now let's look at each one. The first one says Kix is equal to Krx. But what is Kix? Kx is basically the magnitude of in the x direction, which is this. What is Krx? Which is this one. So let me write that Kix is actually the magnitude of Kix vector, that is beta 1 sine theta I. Krx is equal to the magnitude of Krx is equal to beta 1 sine theta r, and both are equal. So beta 1 sine theta I is equal to beta 1 sine theta r, implies your incident angle should be equal to the reflected angle. Okay, and this is the famous Snell's law. Sorry, this is not Snell's law. This is the condition which should be satisfied for electromagnetic wave to propagate from one media to other. Okay. Now let's look at the second condition. What is the other condition? It says that the incident vector should be equal to the transmitted vector. Okay. So the incident vector Kix is equal to beta 1 sin theta I and the transmitted vector along x is beta 2 sin theta t. And both should be equal. So I can write beta 1 sin theta I is equal to beta 2 sin theta t. Remember, this we are considering for lossless medium. Okay. Now for lossless medium, beta is omega into root over mu 1 epsilon 1. This we have already derived. And beta 2 is omega root over mu 2 epsilon 2. Okay. So if I take the ratio of sin theta I theta t by sin theta I, this is equal to beta 2 by beta 1, and this is equal to root over mu 2 epsilon 2 this is beta 1 by beta 2. So this is equal to mu 1 epsilon 1 by root over mu 2 epsilon 2. Okay. And this is actually the ratio of the velocities of the wave in other medium. So U2 is the phase velocity of wave in medium 2, and this is the phase velocity of wave in medium 1. So you see that the ratio of the phase velocities of the wave is dependent on the angle of incidence. The ratio of sine of transmitted angle to the sine of incident angle is the velocity of the wave in the second medium to that of the first medium. Okay. Now let's cross multiply. Let's make this to the top, make this to the bottom, and let's cross multiply. So you see root over mu 2 epsilon 2 sin theta t is equal to root over mu 1 epsilon 1 sin theta I. Now let's multiply by c on both sides. So c into root over mu 2 epsilon 2 sin theta t is equal to c into root over mu 1 epsilon 1 sin theta I, where c is the velocity of the light. The expression c into root over mu 2 epsilon 2 is equal to the refractive index of medium 2. And c into root over mu 1 epsilon 1 is equal to n1 is equal to the refractive index of medium 1. So I can write n2 sin theta t is equal to n1 sin theta I, and this is our famous Snell's law. Okay. So we have already told that root over the ratio of velocities of the two medium is dependent on the incident angle. So we can also define u2 as 1 by root over mu 2 epsilon 2 and u1 is equal to 1 by root over u1 epsilon. So this is the general case where we have considered a lossless media. The wave is traveling in some arbitrary direction. It is incident on the boundary. It gets reflected and gets transmitted, and there is a corresponding angle for each of the reflection. And the wave traveling in an arbitrary direction can be resolved into components along each of the axis, and we know the values of the components of each of the axis. Okay, and then we are looking at the relation, or what is the condition at which, if you define an electric field, it will exist, or what is the condition in which the EM wave exists in both the medium. And the condition is that when the wave is incident on the said plane, the propagation vectors in the x and y direction should be equal for both the medium. That means the incident, reflected and transmitted x components will be equal. The incident, reflected and transmitted y components will be equal. So when you substitute the values of the components in the equations, we found that the incident angle should be equal to the reflected angle, and the multiplication of the refractive index with the sine of transmitted angle is equal to the product of refractive index with the sine of incident angle. Okay. So these are general terms. Next we are going to see is, if we have the electric field in one particular direction, for example parallel to the plane. Okay. So here you should also see that the wave is actually incident on the plane like this. So this is the plane, which will extend to infinity, and there is a corresponding plane here. Okay. The wave is incident on this plane. Now there is one more plane which is actually the plane of incidence, and the plane in which the wave is actually traveling. So that is this plane. Okay. So the wave is traveling in this plane, because you see the wave is in this plane, and it is getting reflected in this plane, or it is getting incident on this plane. Okay. And this plane where the wave has its vectors is called as the plane of incidence. Okay. And this plane is the plane in which the wave is incident on the boundary. So this is the plane in which the wave is incident on the boundary. Although it might get clumsy. So these are the two different planes. Okay, fine. So we will stop it here. We have a parallel continuation of this topic also that we will discuss in the next lecture. Thank you.